Hello everyone, welcome to the second class. Today we are going to discuss together or continue discussing together the semiconductor materials. So in the last session, we discussed the intrinsic and extrinsic semiconductor materials. Just a quick revision for what we discussed the part of the extrinsic semiconductor. So we mentioned that the intrinsic semiconductor consists of just one semiconductor material, which is the silicon, for instance. And if you would like to make extrinsic semiconductor material, so we make topping for another semiconductor material. So for instance, here we have another element called phosphorus. So the phosphorus is added to the uh, silicon, and there is a different number of electrons in the last shell. So the phosphorus has 15 electrons, so the last shell has 5 electrons. The silicon has only 4 electrons, so this means you will have one free electron, which is gonna initiate the current at the room temperature. So from this point, we said that here we have now extra or more free carrier that can allow more current to flow in the semiconductor material. So we discussed one element, which is phosphorus along with silicon, and we mentioned that this is here called a donor material, and this makes N-type material. And also we discussed another example, which is boron, and the boron has only 3 electrons in the last shell. So the boron makes one missed electron, or let's say one hole, and this hole makes the composite as a p-type material. So we call it acceptor, and it's p-type material. And we discussed the concentration. We discussed the concentration of p-type material and the n-type material. Today we are going to continue discussing these points. We will solve an example discussing the current, and we will start in the second slides of the PN junction diet. So let's start with this example together. So in this example, guys, calculate the thermal equilibrium, electron, and hole concentration. So we need to calculate the electron and hole concentration. Consider the silicon at T equals 300 Kelvin, room temperature, doped with phosphorus at concentration of N donor equals 10 to power 16 cubic per cubic centimeter. So this is the concentration of our carrier. So in order to calculate this concentration, so the concentration of electrons and holes of this silicon phosphorus material, or the combination of silicon phosphorus. So we need now to have some constants. So from the previous example, guys, we knew that Ni equals 1.5 times 10 to power 10. So this is from the previous example. This is the electron concentration of silicon. And since this is donor type material, so this means N donor is going to be much more greater than the Ni. So in this case, we can consider that NO equals almost ND. So this is going to be 10 to power 16. In order to calculate now the PO, or the hole concentration, so the hole concentration from the equilibrium relation equals Ni squared divided ND. So we know that ND now equals 10 to power 16. So since the donor has N to power 16, and this is equals to the almost equal to the electron concentration. So this means the whole concentration is going to be Ni squared divided Nd. So the Ni equals 1.5 times 10 to power 10 square divide 10 to power 16. So this means the whole concentration is going to be 2.25 times 10 to power 4. So can you compare, guys, the numbers? So the whole concentration in this material is 2.25 times 10 to power 4. Okay. And as you can see, the electron concentration is much higher. It's 10 to power 16. Okay. So the comment here in this example is in the semiconductor doped with donors, the concentration of electrons is far larger than that of holes. As you can see, the electrons concentration is 10 to power 16, and the whole concentration is to 10 to power 4. So this is a numerical example just to show you how to calculate the concentration of holes and electrons in this material. Assume here now we have another material, so consider silicon at T equals also 300 Kelvin, doped with boron. So this is now acceptor. It's not donor. So this is going to make P-type material here. So he mentioned here, guys, that the doped with boron at a concentration of N acceptor equals 5 times 10 to power 16. So since this is P material now, so we expect that the whole concentration is going to be much higher than the electron concentration. So we can assume approximately that the whole concentration equals to the doping concentration, which is 5 times to power 10 to power 16. And let's apply the equilibrium equation again. So the electron concentration is going to be the intrinsic concentration square divides N acceptor. So we know that for the silicon, the intrinsic semiconductor of silicon, the concentration is 1.5 times 10 to power 10 at 300 degree Kelvin. So this value squared divides 5 times 10 to power 16, which is the whole concentration of the P material. So this is going to give us the electron concentration here, which is 4.5 times 10 to power 3. And the comment here also, in a semiconductor doped with acceptors, the concentration of holes is far greater than that of electrons. So this is what we can expect, guys. For a p-type material, the whole concentration is going to be much higher. And in n-type material, the electron concentration is going to be much higher compared to the other electrons or holes according to the p or n material. Okay. Now, we got the point of the meaning of intrinsic and extrinsic. Let's move to another part now, guys. How a current can flow in a semiconductor material. Just a moment. I'd like to be sure the recording is working correct. Okay, it's working good. Okay, so now, guys, we need to know how the current flow in a semiconductor. In the previous class, we could see a video together that represents the current flow against the electrons. Let's see today what the two parts of currents we have in a semiconductor material and how the current is flowing in a semiconductor material. So, firstly, let's have our pointer here. Firstly, if positive charges or holes or negative charges electrons move in a material, this means a current is generated. So once you have flow of electrons or holes, or let's say any charge, any charges, any charges move in a semiconductor material, so this means the current is flowing or generated. These charges, these charged electrons and holes are simply referred to as carriers. So we call it carriers. So if I say we have carriers, so these carriers can be positive holes or negative electrons. So once we have carriers in a semiconductor material, so this means there is a current flow. But what are the currents, different current flow in a semiconductor material? So the two basic processes which cause electrons and holes to move in a semiconductor material are called, first one is called drift, and it will contribute what's called drift current, and another phenomena called diffusion, and this diffusion will be responsible of having what's called diffusion current. So we have two different currents in a semiconductor material: drift current and diffusion current. And the total current is going to be the summation of both of currents of a semiconductor material. So what is drift? Drift current or drift phenomena, which is the movement caused by electric field. What is the diffusion? Diffusion, which is the flow caused by variations in the concentration of a semiconductor material, or the concentration gradient. Gradient, it's like change in concentration, but not versus time. It's going to be versus distance of a semiconductor material. So we call it gradient. So gradient is gradient for any variable, guys, is different than time change or rate of change. So gradient is change versus x, but time change or the rate of change is change versus t. Okay, so this is d by dx, gradient is d by dx, and rate of change is d by dt. Okay, so let's see together, guys, the two different types of currents we have in a semiconductor material. Start with the drift current. So we mentioned, guys, that the drift current is mainly caused by electric field. Yes, electric field. I know some of you now ask what's the meaning of electric field. So let me just refresh your knowledge, guys. Electric field is nothing but when you apply a voltage across any material. So what is the electric field? Electric field is nothing but volt per distance. Volt per distance. So if you apply a volt on a conductor has a length d, so we can say E equals V divide V. Okay, so E is voltage divide distance. So this is electric field. So once we apply electric field on a semiconductor material, this will cause a current flow, and the current is gonna be called drift current. Drift current. If you have a look here on this block, so if you apply a voltage in this polarity, and this is gonna be now the direction of the electric field, so we expect that electrons are gonna move on the opposite direction. So all of the time, guys, electrons are moving in the opposite direction of an electric field. So we expect that the current, this is also another rule you have to know, the current is, or the current flow for any kind of material is going to be from positive to negative, which is the opposite direction of the electrons flow. So the the voltage or the electric field and the current direction are going to be the same, but the electron direction is going to be in the opposite direction. Let's find the relations. So the electrons acquire a drift velocity if we apply electric field to a material. So the electrons will start moving in a certain speed. So this velocity here is measured in centimeter per second, and this velocity equals, so VDN is drift velocity of electrons, equals minus, because it's opposite direction of the electric field, mu n times E. So E is the electric field applied, and mu n is the mobility of electron. So mu n is constant, called the electron mobility, and the units of this electron mobility is square centimeter per voltage second. And you know that V divide distance, or V per meter, is the electric field units, and the speed is going to be centimeter per second. But here it seems, since this is in centimeter per second, so E has to be also V per centimeter. Okay. So, and here, guys, this is the definition of mu n. So mu n is called electron mobility. And in order to calculate, guys, now the amount of current, so the current is going to be referred by current density. Current density means current per unit area. So the electron drift produces a drift current density called Jn. So Jn is the current density, or current per unit area. So this is measured in ampere per square centimeter. So we measure it here, guys, in centimeter, not in meter, because you know that all dies of semiconductors are very small. So we consider the unit length here as a centimeter, not a meter. So how to calculate now the value of current density? So current density equals minus E. We will discuss now what is E, times N. N is our concentration we calculated before. V dN, which is the drift velocity of our electrons. If you substitute V dN from this relation here as a function of the electron mobility and the electric field, so you will end up with Jn equals plus E times N times mu N times E. What are the definitions again? N is the electron concentration per cubic centimeter, and E is called the magnitude of the electron charge. So it's constant, called the electron charge, and this will be given as well. So electron charge times electron concentration times electron mobility times electric field. So can you see, guys? Electron charge is constant. Mu n is constant. So we can say that the current depends mainly on the concentration and the applied electric field. So these are the, let's say, the important variables that control the current density in a semiconductor. E depends on external disturbance, because this is going to be the applied volt. However, N depends on the semiconductor material or manufacturing. So if you would like to have a semiconductor material with high current, you can control that by means of concentration. For sure, if you apply more voltage, more electric field, you will get higher current. However, this is external effect, not internal effect, which means as a manufacturer, we take care of the concentration in order to achieve a certain current value. And by the end, voltage will be given as like limits of a certain semiconductor die or a certain switch. Okay, guys. So this is very important, guys, to know here. The concentration is the main effective or dominant variable that affect the current density of a semiconductor material. Okay, Now, the drift current is the opposite direction from the flow of negative charge. So as we mentioned, the current is flowing in the opposite direction of electrons and is going to be the same direction of the electric field. So this means, guys, the drift current in an N semiconductor material is the same direction as applied electric field. Okay, so this is the conclusion here from the drift current in N type semiconductor material. Let's see what about the P type. So for a P type material, the relation is going to be VDP, the speed, equals VDP equals mu P, which is the mobility of holes times electric field. By the same way. However, the sign here is plus sign because holes will flow in the opposite direction of electrons because it's positive charges. So in this case, the hole drift current can be calculated as E, which is electron charge, times P, which is the hole concentration, times VDP, which is the drift velocity of holes. Substitute with the drift velocity, mobility, and electric field. So you will end up with E P mu P E. E, little e is the electron charge, it's constant. P is the hole concentration of the p-type material. Mu P is the hole mobility of the p-type material, and E is the applied electric field. So again, guys, the current density in p-type material has one dominant variable, which is the hole concentration. So this is very important note as well. And as you can see here, guys, by the end, the conventional drift current is the same direction as the flow of positive charge, because we said that the positive charge is opposite direction of electrons, so it will have the same direction of current, which means by the end, the drift current in a p-type material is also in the same direction as applied electric field. So these sentences or these quotes are very important, guys. So you can find it simply in the exam as fill in blank or in multiple choice or true and false. So please, you have to understand the basics and the theoretical background for every semiconductor material. It's not only numerical problems. You have to understand the theory as well. Okay. Okay. Great. So this is now the drift currents. What about the overall drift current now if we have PN material? What's the meaning of PN material? Will we have P and N together? Yes, we will. So in all of power electronics and the electronic semiconductor switches, we use P and N together. We use P and N together. And we will see this most probably by the end of our class today when we discuss the PN junction. Okay, guys. In order to get the overall drift current now, we need to summate all the drift currents from electrons and from holes as well. So simply we can say now J, the total current density, equals the drift current due to electrons plus drift current due to holes. So it's En mu Ne plus Ep mu Pe. So E is a common factor. Little e N mu N, little e P mu P can be defined as together as sigma or summated together in this sigma or 1 divide rho. So what is sigma and what is rho? We will give a definition for these variables now. So sigma is E m mu n plus E p mu p. So we call it sigma. What is sigma? Sigma, guys, is the conductivity of a semiconductor. Conductivity of a semiconductor material. So we can say this semiconductor material is a good conductor by means of the value of sigma. And sigma is measured in ohm centimeter minus 1. So ohm centimeter minus 1. So this is the conductivity of a semiconductor material. The opposite of the conductivity, you know that from electrical circuit, the opposite of conductivity is called resistivity. So the resistivity is 1 over conductivity, so it's going to be measured in ohm centimeter. Ohm centimeter. So this is the resistivity of a semiconductor material. So if the resistivity of the semiconductor material is small, so this means you have high quality semiconductor material. But if the resistivity is high, so this means you have low quality semiconductor material because the losses will be more high in this semiconductor material. Later on, we will discuss the losses within semiconductor material. So at this point, guys, we can say if the electric field is a result of applying a voltage to a semiconductor material, then the above equation become a linear relationship between current and voltage, which is referred to as Ohm's law. So Ohm's law by the end, you know Ohm's law for DC equals V equals R times I, and this is a similar relation here from R. So by the end, R is ohmic value. So you just need to know the dimensions of the semiconductor material in centimeter in order to get the resistance value. So by the end, this is a linear relation now for our semiconductor material. Okay, so this is now the drift current. Let's solve an example together, guys, just to make application for this part. So in this example here, we need to calculate the drift current density for a given semiconductor material. The example says, consider silicon at T equals 300 Kelvin, doped with arsenic atoms at concentration of Nd equals 8 times 10 to power 15 per cubic centimeter. So this is the donor concentration. Donor concentration, is it going to be N-type or P-type, guys? Yes, right. This is going to be N-type material because this is a donor material. Assume the mobility values of mu n equals 1350 centimeter square per voltage second and mu p equals 480 centimeter square per voltage second. And assume that the applied electric field is given by 100 volt per centimeter. So this is the voltage we have. We have the electromobility, the Hall mobility, and we need to calculate the current density. So in order to calculate the current density, we need to calculate sigma. We have electric field, and sigma, you know, it depends on the some constants like electron charge and mobility. We have the mobility here, and also the concentration. So we have the concentration, and we are ready now to make all of the calculations. So here, guys, we mentioned here this is a donor material. Donor material means this is N-type material. For N-type material, guys, you can make a complete calculation, but it's not making sense to make a calculation with a difference or with very high difference values, because by the end the result will be just depending on one variable of them, because the difference is very high between the P and N concentration of the material. So since this is an N-type material, this is a donor material, So we can neglect the effect of holes. So let's consider only the effect of electrons here. So since the donor concentration is given by 8 times 10 to power 15, so let's consider this only in our relation here. So we can calculate now, guys, the whole concentration. So the whole concentration is Ni squared divided Nd. You know that for our semiconductor material, the intrinsic concentration of the silicon is 1.5 times 10 to power 10. Actually, here, guys, it's not given in the example, but in the exam, if you have this equation in the exam, I will provide you with the value of the intrinsic semiconductor concentration. So the intrinsic semiconductor concentration is 1.5 times 10 to power 10, and you have Nd equals 8 times 10 to power 15, so you can easily calculate the p-type material. When you calculate the sigma now, so sigma equals E mu n times n plus E mu b times p. But again, we said this part is going to be very small. Can you see, guys? 10 to power 15, 10 to power 10. When you add these two numbers together, it will give you the same number. So it doesn't make sense to use it now. So we can say, assume that the p-type material effect is neglected here in this part of the question. So we can assume that sigma here is almost equals to E mu n times n. So E is the electron charge, it's constant. The mobility of electrons is given here 1350, and the concentration, it's given also 8 times to 10 to power 15. So this is going to be 1.73 ohm centimeter minus 1. So this is now the conductivity, guys, due to the N type, because this is a donor material. If you would like to calculate the other part, it's up to you, but by the end, it will not be effective in our results. So this is now the sigma. We would like to calculate the current. So simply, we need to multiply this time the electric field. So we can say J, or current density, equals sigma times E. So 1.73 times 100 volt per centimeter. So this will give us 173 ampere per square centimeter. Can you imagine, guys, now? The silicon arsenide, this N-type material, can carry up to 173 ampere per square centimeter. So this is the meaning of calculating the current density of this semiconductor material. Okay, guys, by the way, this is not very high value. We have much higher values now in modern technologies in semiconductor materials. Okay, later on, guys, we will open some data sheet together, but this is very late time in our classes, maybe in week number 10, when we have some applications starting the project. So we will open together data sheet of some semiconductor material and see these parameters in data sheets. Okay. So this is now the current calculation, and how can we calculate the current for this material. The other part of current. So we mentioned, guys, that we have two different parts of current. One part depends on the electric field applied, and the other part actually is called diffusion current, and this depends on the concentration, or the difference in concentration in a semiconductor material. So in the diffusion process, particles flow from a region of high concentration to a region of low concentration. So this is the nature of the semiconductor material. The parts are going to move, or the particles will move from the region of high concentration to the region of low concentration. So the diffusion of electrons from high concentration region to low concentration region produces a flow of electrons in the negative x direction. So if you assume that this is x direction here, guys, and you have electron diffusion moving in the opposite direction here like that, so the current direction is going to move in the opposite direction like that, because you know that we mentioned the current is flowing all of the time in the opposite direction of electrons. So we can say now, guys, the diffusion current density equals E, which is the same constant, the electron charge, times a new variable here. We have dn. So dn is referred to as the electron diffusion coefficient. It's constant. Okay, times dn by dx. So dn by dx, guys, is the gradient of concentration of electrons in the material. So this is the current density. So the current density again equals the electron charge times the dn, electron diffusion coefficient, times d by dx of n, where n is the concentration of the electrons in our material. So again, d by dx or dn by dx is the gradient of electrons concentration in our material. Okay, guys. So this is the definition of the diffusion current here. What about the p material? So the p material is going to be the opposite. So the Jp equals minus EdP times dP divided dx. Why? Because you know that whole diffusion is opposite to electron diffusion. So this is going to be the opposite. So by the end, the total current for sure should be the summation of the two diffusions. Okay, so the diffusion current is a function of the distance of the semiconductor material, which means along with the semiconductor material, the density is going to be different. And then the overall current density in the semiconductor is the sum of the drift and diffusion currents. So after calculating the two parts of diffusion and drift currents, the total or the summation is going to be the total current in the semiconductor material. The diffusion and drift current densities are referring to the capacity of semiconductor to carry electrical current. And this is the meaning of current density. Okay, guys, let's solve this example together here. So here, we need to calculate the diffusion current density for a given semiconductor material. So consider a silicon at T equals 300 Kelvin and assume that electron concentration varies linearly from N equals 10 to power 12 to N equals 10 to power 16. So these are the two different concentrations of the material we have in a certain distance of a semiconductor. What is distance given here? Over a distance from x equals 0 to x equals 3 micrometer. So from 0 to 3 micrometer, the concentration were 10 to power 12 and changed to 10 to power 16. So this is the diffusion we have here in this part. Over the distance from x0 equal to, assume that dn equals 35 centimeters square per second. So we need now, guys, to calculate the current density. So it's direct substitution in the relation. So here, this is our material, and this is N material. So simply we can say now Jn equals EdN times the ingredient of concentration. So E is given 1.6 times 10 to power minus 19. And again, if it is not given here, it's constant and will be given in the exam. The dn is given 35 centimeters square per second, and the gradient, we can calculate the gradient easily. So he mentioned here, guys, the concentration is varies from 10 to power 12 to 10 to power 16 from 0 to x. So you have to respect the direction. So this is the variation from 10 to power 12. So this is at x equals 0, and that is to 10 to power 16 at x equals 3 micrometers. So 10 to power 12 minus 10 to power 16 divide distance 0 minus 3 times 10 to power minus 4. Okay, so this is the distance we have. You know, micro, guys, is 10 to power minus 6, not 10 to power minus 4. Why we multiplied here times 10 to power minus 4? Hmm? Yes, I'm expecting you answer this correctly because all the dimensions here are in centimeters. So when in micrometer, you should multiply times 10 to power minus 4. So please, guys, don't forget the conversions. So micrometer is 10 to power minus 6. This is correct to convert to a meter, not to a centimeter. So centimeter here, we need to multiply the micrometer by 10 to power minus 4. If you calculate that, guys, so the Jn equals here 187 ampere per square centimeter. So it's very straightforward example, guys. Okay, just to show you how to calculate the uh, current due to diffusion in any semiconductor material. So this was the part we need from these materials now. So the summary of these materials, guys, in these slides, we learned the following: the types of materials, the insulators, conductors, and semiconductor materials. Also, the atomic structure of elements. We learned that in the last class. The intrinsic and the extrinsic semiconductors, and the current capacity of a semiconductor material. Now, we are ready to mix p-type material along with n-type material in one composite to see what's called p-n junction. So let me start now in the other materials here. I will share all the materials with you on eCampus. So here, guys, in this material, the objective is to determine the properties of a p-n junction, including the ideal current voltage characteristic of the p-n junction diode. What's the meaning of p-n junction? What's the meaning of voltage current or current voltage characteristic? What's the meaning of p-n junction diode? You will learn all of that in this material. Firstly, let's see what will happen if we add p and n junction together. So let me have my laser pointer here. Okay. When the p-n junction is formed, guys, when you bring a p material and n material together, what will happen? The free electrons in the n region begins to diffuse across the junction and combine with the holes in the p region near the junction. So from the beginning, guys, so as you can see, this is the shape. P region has holes, n region has electrons. So what happens is the, let's wait a bit to start from scratch here. Yes. So the electrons are gonna move to the holes in the p region. And at the same time, the region will be constructed here in the middle. So again, the negative charges came here, the positive charges will be attracted to the negative charges here, and this is gonna make here a region in the middle. This region here, guys, we call it depletion region. Depletion region. What the depletion region now, guys? Depletion region is acting like a region that cannot flow electric current. In order to allow a current to flow, you need to break this region. So when you bring p junction and n junction together, or p type material and n type material together, in the middle you will have what's called p-n junction. So this junction is made because electrons will move from the n region to the p side, and at the same time the holes will be concentrated along with the electrons from the n region side. So this will make a region called p-n junction. And again, this PN junction or this depletion region will not allow a current flow. You need to break this region firstly in order to allow a current to flow in this material. Okay, guys? So the discussion again here, this makes the N region lose free electrons and create a layer of positive charges near the junction. So this, the positive layer charge created in this side. And as the free electrons combine with the holes in the the P region also lost holes and create a layer of negative charges near the junction here in this part. So the two layers of positive and negative charges create a region where charge carriers are uh, depleted. This region is called fittingly the depletion region. So this region, guys, is called the depletion region. And again, this depletion region will not allow any current to flow. You have to break this region firstly. Okay, so this is what's called the formation of a p-n junction. So we understood now when we have p-type material and n-type material, we can combine them together in order to have p-n junction. Let's make it more in deep and give the mathematical representation of this p-n junction. Because of the electric field in the space charge, guys, so you will have electric field if you apply electric field in the material. Okay, so there is a potential difference across the region, that region. So this is the region here, guys. So you will have a voltage difference between the P or around the depletion region of our material. So this is the N side, this is the P side, and this is the depletion region. And the potential is, as you can see here, this is 0 for instance, and this is higher. Or let's say instead of 0 and higher, this is level 1 and this is level 2. So in order to break this region, you have to make a voltage higher than this volt. So if you apply a voltage higher than this volt of the barrier, you will be able to flow a current in the p-n junction. Okay, guys? So this built-in potential barrier, we refer it, by the way, in all of the semiconductor material as the turn-on volt. Turn-on volt means the voltage required to turn on the junction inside the semiconductor material. Okay, so here in this textbook, we referred here to this by the voltage barrier. Okay, so what the voltage barrier now? Actually, it depends on these parameters you have here in the relation. So VBI, the voltage barrier, equals K times T divide E. K is Boltzmann constant. T is the absolute temperature in Kelvin. E is the electron charge. Logarithm Ln Na times Nd, and you know for sure Na and Nd are the acceptor and donor concentration of the p and n type regions, divide Ni square, which is the intrinsic concentration of the semiconductor material. So since this is Kt divide E, all of these are considered constants in the room temperature. So let's say this is going to be Vt. So Vt is the threshold volt. So Vt is called thermal volt, guys. Threshold or thermal volt here. So the thermal, because it depends on the temperature. So we call it thermal volt. So thermal volt, Ln Na Nd divide Ni square. So this is called the barrier volt. By the way, by experience, this barrier volt in most of semiconductor materials is varied between 0.4 to 0.7, 0.8, something like that. Okay, so and we call it turn-on voltage again. So this is called, guys, the barrier volt. Okay, so the parameters Vt is called thermal voltage, and this is approximately equals 0.026 if the temperature is 300 Kelvin. So at room temperature, this VT is gonna be 0.026, 26 millivolts. Okay, guys, let's solve this example together, guys. So now calculate. In this example, we need to calculate the built-in potential barrier of a PN junction. So we have a PN junction, and we need to know what the V barrier of this PN junction. So consider a silicon PN junction at room temperature, 300 Kelvin, doped at Na acceptor equal 10 to power 16 per cubic centimeter, and the P region is doped by Nd equals 10 to power 17 per cubic centimeter. And we need to calculate now the barrier volt. So simply we can substitute in our relation now. So Vt is 0.026. We have the concentration. So when we calculate the barrier of this material, it's going to be 0.757 volt. Okay. Now, let's go more in deep in order to understand the concept of a PN junction. So, if you have a PN junction now, and later on, guys, we will replace the PN junction by just diode, because the diode is nothing but just a PN. Okay. So let's see, guys, in this case, what will happen if we connect the PN junction in different ways. Different ways means what? So you have P and N. The different ways in potential in DC supply is either applying positive to P and negative to N, or the opposite, negative to P and positive to N. So in this case, guys, we are calling this as biasing. So biasing of a semiconductor material means connecting the supply to the semiconductor material. So this is the meaning of biasing. Okay. So let's start with the reverse biasing. Reverse bias PN junction means the P is going to be connected to the negative of our supply, and the N region is going to be connected to the positive of our supply. What will happen? What will happen if we connect the PN junction to a supply in this way? We call it reverse bias. What will happen if you reverse bias the PN junction? So let's see together. For instance, this is P. Let's see from this figure here. This is the P, and the P is connected to N. What do we expect? So this is positive, and this is connected to the N. So if you have here electrons, these electrons are going to move in this direction to be connected to positive. So any negative charge will lead to move in that direction. Correct? And here in the other side for the P, any negative charge, any positive charge will lead to move in the opposite direction. And I think it's clear from here, from this side, guys. So the electric field is applied here. So for the N, or for the negative, electrons are gonna move here in this direction. As you can see here, electrons are moving in this direction, and the holes on the other side, or the P charges, are gonna move in the opposite direction. So what will happen to the PN junction now? Actually, the PN junction distance or layer has been increased. And if the distance is increased, this means the ohmic value of this piece or junction will be increased. And this is exactly what happens in a PN junction. So if you connect a PN junction in reverse biasing, what will happen is the depletion region width will be increased. So the depletion region increase means the resistance will increase more, and this means no current is gonna flow. So this is the reverse bias PN junction. the discussion here, guys, because of the additional positive and negative charge induced in the space charge region with increase in reverse bias voltage, a capacitance is associated with the PN junction. So this is not only increasing the resistance, guys, it makes like a capacitor because all the negative charges will move in this direction and all the positive will move in the opposite direction. So this means now you have two different layers with bigger distance. Bigger distance in between means as like as if it's insulator material. And you know, insulator material between P and N, this means this is equivalent to a capacitor. Okay, so this makes the current flow is much harder in this case. And this is actually the junction capacitance. So the junction capacitance here is given by C junction equals Cg0 1 plus Vr divided Vbi divided to power minus half, where Cg0, guys, is referred to as the junction capacitance at 0 applied volt. So Cj0 is the junction capacitance at 0 applied volt. This means at normal, before of connecting supply, and Cj at a certain supply value, and Vr is the applied volt to our semiconductor material. Okay, so this is called the capacitance of our junction. It's not that important in our calculations for the time being, but what we need to understand here from this part, if you apply a reverse biasing for our PN junction, the depletion region is going to increase, no current is going to flow, or let's say leakage current only will be allowed to flow. Leakage current, we will give a definition for a leakage current later on. It's very, very small amount of current. Okay. And also you will have an increased capacitance or junction capacitance due to this reverse biasing. And this is a direct example to just know how to apply in this relation to our case here. So here in this example, guys, we need to calculate the junction capacitance. If a PN junction of silicon is given, PN junction at temperature of 300 Kelvin with a topping concentration, Na is given 10 to power 16, Nd 10 to power 15, and assume that Ni is given, and let Cj0, the capacitance at 0 volt, was 0.5 picofarad. And we need to calculate the capacitance if we apply a volt of 1 volt and 5 volts. So we need to know the capacitance if we apply two different values of voltages here. So simply, firstly, we calculate the V barrier using our relation. We calculated this before. So for this material, with this concentration, the barrier volt is 0.637. And we mentioned before, it varies according to the material. It can be from 0.4 to 0.8, something like that. Can be a bit higher, a bit lower. So this is the range of the barrier volt for semiconductor materials. And the junction capacitance for Vr equals 1 volt can be calculated as follow now. So Cj0 is given 0.5 picofarad. So we then multiply times 10 to power minus 12 because we will get the value also in picofarad by the end. 1 plus Vr divides Vbi. So Vr is 1 volt, Vbi is 0.637 under root 2. So this is give us the value of the capacitance. So the capacitance is 0.312 picofarad. So at 1 volt, the capacitance is 0.312 picofarad. If we apply 5 volts, so this capacitance is going to be less. It's going to be here 0.168 picofarad. So what's the meaning of that? So as you can see, guys, when you apply voltages, the capacitance is decreasing. So the comment here is the magnitude of the junction capacitance is usually at or below the picofarad range. This is what we could observe. And it decreases as the reverse bias voltage increase. So when you increase the reverse bias volt, the capacitance decreases. The capacitance decreases. Does it make sense, guys? Does it make sense? So capacitance is decreasing. Does it make sense or not? Let me write here just one quick. So what the capacitor relation, guys? You know that capacitance equals epsilon node epsilon RE divide D. So it's not easy to write this here for the time being, but the distance, the relation between C and C is inversely proportional to distance. I think we can insert the capacitance relation here. So insert equation. Okay. Mm, 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 mm. Yes, this is epsilon. So this is the capacitance relation, guys. This is the capacitance relation. So the capacitance equals epsilon. Actually, we have two different epsilons. If you remember this in electrical circuit, guys, epsilon node times epsilon R, okay, the relative and the absolute permittivity of a capacitance times A. A is the area of the plate of the capacitor, the positive plate and negative plate of the capacitor, and D is the distance between the two plates, or let's say the thickness of the dielectric material. So what happened in case of reverse biasing is the distance of the depletion region is increased. So once the D is increasing, so this means C will be decreasing. So actually the results here make sense, because as you could see, guys, as you could see here again, so more volt means the width of the depletion region is increasing. So the distance of the dielectric or the depletion region is increasing. So this means the capacitor will be decreasing. So this is the effect of reverse biasing. Okay, guys. By the way, the opposite will be in the positive, or the forward biasing. So this means this capacitance will be demolished if we apply the positive volt or the forward biasing of our semiconductor material. Okay. So this is just a quick discussion about the reverse bias. Now let's see, guys, what will happen in forward bias. For the forward biasing, what will happen is this is P. Let me open the pointer again. Yeah. So this is P. So what will happen when you have positive charge here? So all positive charges will be the opposite of the negative charges here of the B side. So this means, sorry, in the P side, firstly, before the electric field applied, it's not clear in this figure. So the positive charge of the holes will be opposite sign compared to the positive side here. So it's gonna make repulsion for the charges. So the holes are gonna be moving in this side, and in the other side here, this is negative. So what will happen to the electrons in the N material? So it will make also repulsion. So the electrons are gonna move in this side. So what happen is, if you apply a positive charge or forward bias like that, and if the volt increase over V barrier, what will happen is this depletion region width will decrease. And decreasing the depletion region width means the resistance of the depletion region is decreasing. The capacitance also will increase. Okay. And this means, guys, in this case, you will break your BN junction. You will break your BN junction. And breaking the BN junction means you have a material allowing a current to flow as if it's just a wire. So this is the idea now. We can conclude that our semiconductor material can be controlled to flow current. How? Once we apply a voltage greater than the barrier volt, the wire is gonna the PN junction is gonna work as a wire. But wire is like the ideal case. In reality, we have a certain voltage drop, we have equivalent resistance for sure, but the ideal case will be like a short circuit. So this is a big revolution, guys, in the semiconductor when these semiconductor materials have been invented. So instead of having insulation, you can convert the insulator into conductor by means of controlling the voltage across this material. So this is what happened here for a PN junction. So once you apply a voltage greater than the barrier volt, what will happen? The depletion region size will be decreased and the current will start flowing in our material. So this means here the PN junction can allow a current to flow if the voltage applied is greater than the barrier volt. And what's the current flow relation now? So the ID, the die current, is equals to IS, which is the saturation current, times E exponential VD divide N VT minus 1. What are the different parameters we have? So IS is the reverse bias saturation current. This current is very, very small value. As you can see, guys, it could be 10 to power minus 18 to minus 12. So this is the range of this current value. This is called the leakage current in the reverse biasing region. Okay, and this, what we said, it's not completely isolation, but you have a leakage current. This is in reverse biasing. And the other parameters we have here, VT is the thermal volt, and you know it's equal 0.026 volt at the room temperature. And the other parameters, N is called emission coefficient, guys. So N here is not referring to the electron concentration. This is another variable. It's called identity factor, and this factor is almost between 1 and 2. And unless otherwise stated in any problem, we will consider it equals 1. So this is for this N. Okay. So this is the relation of our die current of the PN junction. Okay. So this is the ideal current voltage relation. If you draw this relation, or we can draw this relation in another slide, but let's here solve this example together just to imagine the current flow according to the voltage applied to our PN junction. So here, guys, we need to determine the current in a PN junction diode at different operating conditions. Let's see. Consider a PN junction at T equals 300 Kelvin, room temperature, in which IS is given, the saturation current is 10 to power minus 14 ampere, and N equals 1. This is the ideality factor. And we need to find the current at VD equals 0.7 and VD equals minus 0.7. Let's see. So substitute in our relation now, guys. Is times exponential Vd divide Bt minus 1. So we consider n equals 1 here. So substitute in the equation, you will get Id equals 4.93 milliampere. So if you apply a current, a voltage of 0.7, this is going to be the amount of current. What's happening if you apply minus 0.7? Substitute in the relation at minus 0.7. So you will get that this value is almost zero. This value is almost zero. Exponential minus 0.7 divided 0.026, it's zero. So this leads to the current is going to be minus 10 to power 14, which is nothing but the saturation current. So why we have here the saturation current? Because Vd is negative, which means it's reverse biased. So the mathematical model actually now matches the theoretical background we just discussed. So positive volt will allow a current to flow. Negative volt will allow only the leakage current to flow, or let's say it's gonna be ideally like open circuit. Okay, guys. So this is just a quick application for our current relation. So now, guys, if we would like to draw the characteristic, the IV characteristic of the diode, so we will just give a quick hint now, and we will discuss it more in deep in the next class. So we said in the forward biasing, so forward biasing means voltage positive, and this is the current here. This is the positive value of current. So there is no current flow, or the current flow can be very small value during the voltage less than barrier volt. And once the volt is greater than the barrier volt, a current will flow with higher values. Okay, so this is a PN junction diode. So now the diode is nothing but P and N together. The current flow is going to be all of the time from the P to N type, from the P to N, and the P is called anode and N is called cathode. So the positive or P type terminal is referred to as anode, and the N type is referred to as cathode. Okay, and the current is going to flow in this direction, and the voltage drop across the diode is going to be Vd by this polarity. So this is called here the forward biasing characteristic, and the reverse biasing characteristic, you will have just the minus Is value for the negative volt, but this characteristic is incomplete. We will discuss more about the characteristics in the next class. Thank you, guys. Have a nice weekend, and have a nice long weekend, and see you in the next class. Thank you so much.